Let's continue our discussion of representation of numbers. So in this section, we're going to talk about finite precision calculations, which corresponds to the representation of numbers in computers rather than the exact representation and the exact calculation that happens mathematically. So as we said before, when we represent numbers in Python, there's two basic approaches, two fundamental numerical types that we have built in, the integers. And we said before that some languages have a specified number of bits for integers, so there is a maximum and a minimum integer that is much smaller than is the representation if we are using Python. In Python, the integers are limited by the amount of memory we have available. And so there's still a maximum and a minimum, but it depends on the particular computer and the amount of memory that's available there. But in these cases, as long as all of our calculations stay within range, Python integers behave the same way as mathematical integers. Floats, on the other hand, numbers with a decimal or a fractional portion, we should say fractional because if we're using binary numbers and so on, decimal portion doesn't make sense, but the fractional portion is very different in terms of the computer representation versus a non-computer representation. So we're going to describe portions of the IEEE 754 floating point arithmetic standards. Not all of it, we're not going to go into all of the detail, but enough to get a good idea of what is happening with the computer and why things don't behave the way we might expect. So the standards include the formats for binary or decimal representations. There are single formats, which correspond to a 32-bit representation, double, which is a 64-bit representation, and then there are 128-bit representations for both, and for binary, a 256-bit representation. The standard includes how to interchange formats. It includes different rounding rules. We'll talk a little bit about that. The operations that are expected to be implemented. So basic operations, plus, minus, multiplication, division, some trigonometric functions, specific functions that are clarified and said specifically these have to be included if you're going to claim implementation of this standard. We're not going to go much in that direction. We're just going to look at what happens with numbers under even more routine kind of calculations. Adding and subtracting, multiplying and division are enough to see that the floating point arithmetic is different than the exact arithmetic that we might be used to. And then exception handling, how to handle when there is an error of some type. So division by zero errors, other kinds of things are specified in the standard, how they need to be handled. So before we get into the full version of the IEEE standard, we're going to look at a simplified, what's called a toy version of the calculations that allow us to see what is going on and what is happening in simpler examples rather than the full-blown version. Then we'll look at the full version and see what happens and how these situations that we've seen, how they correspond and how they appear in the full floating point representations. So what we're going to do in this simplified version is we're going to represent a number x in a decimal representation, but we're only going to have 3 digits possible. So x is going to be plus or minus, and then there will be a d0, and then the decimal point, and a d1, d2. So 3 digits, and then times 10 to an exponent. So we will have small numbers if e is a negative value, numbers close to 0, put it that way. And then if e is negative, we get those numbers close to 0. If e is positive, we get numbers that are further away from 0. And so there are conditions on the d values. The number before the decimal point needs to be between 1 and 9 in this representation, including 1 and 9. The d1 and d2 values, either or both, can be 0. But again, the biggest they can be is 9. And then the exponent itself is allowed to be -9 up to +9. And that includes 0 in between. So there are a lot of different numbers, and we'll count those in a few minutes, of how many numbers are possible and what we can represent. So this is the idea of what happens in the full standard, that there's a specific way that numbers are represented, and it's limited in terms of how much memory is available to store the different values. So this simplified version comes from section 2.7 of a rather famous, at least mathematically, famous textbook called Matrix Computations. Four editions of that book over the years. And it was written by Gene Golub of Stanford and Charlie Van Loan from Cornell. So in the toy representations, if we have a number such as 7, the number 7 is going to be represented as 7.00 times 10 to the 0th power. 10 to the 0th power is 1, and this corresponds to 7 times 1. So that is how the number 7 would be represented in this simplified version. A number like 5400 would be written as 5.40 times 10 to the 3rd. That would allow us to write this number in this simplified version. A number like, what is this, 768 million would be written as 7.68 times 10 to the 8th. So all of these are exact values, and the representation matches the number exactly. If we had a number like -0.134, we could write that as -1.34 times 10 to the -1st power, and again, that's an exact representation of that value. But if we look at a number like pi, pi has more than 2 digits after the decimal point, but we're only able to record 2 of them, so we might record that as 3.14 times 10 to the 0th power. So in that case, pi's representation is not exact, but it is as close as we can get using this particular numerical representation. Then if we had a mixture, we have some numbers that are written in this notation, and we add them together. Well, if we add these two numbers together, then the value that we end up with, 1,275,600, we can't represent that number exactly, so we would probably round that to 1.28 times 10 to the 6th. We'll talk about some rounding things. There's other ways to round that are possible as well, but that would be this most standard, the most typical way of rounding. And so in that case, this addition problem, even though we can represent the two values correctly, the addition we can't represent exactly anymore. We get the wrong answer in that representation. And then if we had this other example with multiplication, the same kind of thing happens. We can come close, but we have to round the value to be able to store it in our simplified representation. And then if we look at a number like 0, we had the condition that the D1 and D2 could be 0, but the D0 value, the one to the left of the decimal point, can't be 0. And so in the representation as we've described it, we cannot describe the number 0 at all, because we're going to have at least some value there that's not 0. So what usually happens then is we give a special dispensation. We say, okay, if you're talking about 0, you can write that as 0.00 times 10 to the 0th power. And that's the only number that's allowed to be written in that way. Of course, we also have the plus or minus, and so the situation can arise that we are thinking of there being a positive 0 and a negative 0. In this situation, we have a single value, but the value can have different representations. And in the IEEE standard, there are things related to, you will use the plus 0 will be the output at certain points, and the negative 0 will be the output at certain points, and that will help with the exception handling, with the error handling that we talked about, some other things that can happen. So that standard does treat those separately, same value, but separate representations for different reasons. We don't need to get into all of that, but there is a bit of care that's needed at that point. So we can represent 0 in our simplified version by allowing this distinction to the rule in this one particular case. So why do we rule out the D0 equaling 0 except in this one special case? Well, the idea here is that in this toy representation, something like 0.10 times 10 to the first is the same thing as 1.00 times 10 to the 0th power. And so part of the idea is that in certain representations, we want numbers to only be able to be represented one way, to have a unique representation of that number. It doesn't hold all the way through the standard, the IEEE standard, and when we go into more detail, does allow multiple representations of some numbers. But in this particular version, the idea is we're trying to limit the number of values that have more than one representation, or to limit it to exactly one representation per number. And if we allow the D0 to be 0, that will give us different representations for some numbers. Again, that's not always a bad thing. Sometimes when we have multiple representations of a number like 1/2. 1/2 we could write as 1/2. We could also write it as 2/4. We could write it as -5 over -10. All of those are 1/2. And it's not bad to have multiple representations always, but sometimes it can be problematic. Sometimes other issues can arise. And so in this particular version of this floating point kind of toy representation, we try to limit those multiple representations. All right, so in this particular case, the smallest positive floating point number that we could have, remembering the structure, would be 1.00 times 10 to the -9th. The exponent can be only as small as -9, and this gives us the smallest number that we can create in this representation. This is not the smallest floating point number that we can create in all, but it's the smallest positive floating point number that we can create with this particular simplified representation. Then the largest positive floating point number that we could have, well, again, we have 3 digits with the decimal point after the first one, times 10 to a power, so the largest one is 9.99 times 10 to the 9th power. And then when we want negative values, we could have the smallest negative value. We put a negative sign in front of the largest positive, right? So the smallest number we're describing is -9.99 times 10 to the 9th. And the biggest number that we're representing is 9.99 times 10 to the 9th. And then the numbers that are close to 0, the smallest positive one of those is this number 1.00 times 10 to the -9th power. So that means there's a smallest, there's a largest, and they're all separated from each other, so we can very specifically go through and list them in order. And if we can list things in order, then we can count them. So how many of these toy floating point numbers are there? Well, this is going to be different than the real numbers, because for the real numbers, there are infinitely many real numbers. And as we'll see later, there's a distinction between different kinds of infinity. Don't worry about that right now, but there are different kinds of infinity. And in the case of the real numbers, this is actually an uncountable infinity. We said with these floating point numbers, we can put them in order. Here's the smallest one, here's the next one, here's the one after that, and so on. There are so many real numbers that we can't do that. And there's a higher level of infinity that we will discuss later about how many real numbers there are and how we can compare those to other things. But for the floating point numbers, there are a fixed number of those. So again, looking at the definition of the pieces, we see that there is a plus or minus at the beginning, so there are two options that happen there. For the D0 value, there are 9 different values that can take on, 1 to 9. For each of D1 and D2, there are 10 values, 0 through 9. And then for the E, there are 19 values, because we can go from -9 all the way up to 9. And so with these choices, 2 choices for the sign, 9 choices for the next, 10 each for D1 and D2, 19 choices for E, and then the special situation of the number 0 that's not part of this description. In all, there are 2 times 9 times 10 times 10 times 19, plus the 1 that represents the 0, 34,201 of these floating point numbers. Way fewer than the number of real numbers that there are, so it's very limited, but this is a lot of different values that we are able to represent using only the 3 digits for the number part and then the 1 digit for the exponent. Okay, but there are some issues that are different with these as well. Not only are there a limited number of them, and a largest and a smallest, but we have different spacing between these different numbers. So in this description that we have, some numbers are closer together than other numbers in the ordering. When we order the numbers and write them in order from smallest to largest, some numbers are closer together than others. Some numbers can be described exactly. We saw some examples where we could describe numbers exactly. We saw some examples where we couldn't describe the numbers exactly. We would have to round to get there. But then we have some numbers that can't really be described at all. If we have numbers that are outside this range, then what happens? The number's too big or the number's too small. And so in the toy representation, in this simplified version, we can't describe those numbers at all. And that same problem will carry over into the IEEE floating point representations, that some numbers can't be described at all. They're outside the range, and we'll talk about that. So just as an example, what if we had something like 1.23 times 10 to the 4th, and we multiplied that by 4.56 times 10 to the 7th? Both of these numbers are perfectly valid in our representation, but when we multiply them together, we need the portion with the times 10 to the power needs to be an 11, and we're only allowed to go up to 9, so this number is too big for us to represent. Both numbers individually are fine, but the final answer is too big to represent. And so this is a number that the pieces are fine, but the combined value, the product, is too big. All right, so we're going to specifically talk about the 64-bit standard. This is the double format for the IEEE values. Now, real calculators and computers do things slightly differently, and we will describe the general sense here. There are more digits or bits in the 64-bit standard or in the other standards than in our toy version that we just went through. So for a 64-bit floating point representation of a number x, the idea is that we have x, again, as our value, and it's going to be plus or minus. And now there are 11 values that we're going to call by the name A. So A1, A2, up to A11. These are just binary values. These are bits, zeros and ones. And then there are 52 values that we're going to call the B portion of things, and we'll describe in just a second what those mean. But this is all just one number, but the number itself will describe what we are describing overall with the value. So we have a bit for the sign, and for the sign we're saying, is there a negative sign there, yes or no? So if we put a 0 at the beginning of our value, that means positive. There is no negative sign. And if we put a 1 at the beginning, that means that the value is negative. So here we didn't write this as a bit, the plus or minus, we wrote it as a symbol, but it's really another bit. It's 0 or 1. Then there are 11 bits for the exponent, and then 52 bits, B1 to B52, for what is called the mantissa. This is the part that's in the base. We'll see in just a second where this portion comes into play. All right, so what do we have? We have 1 bit for the sign, 11 bits for the exponent, 52 bits for the mantissa. That gives us the 64 bits in all that are used to describe the number. Okay, but describing a number in this way isn't very helpful unless we can then calculate what that number is, or the meaning of this binary value that we've created. So the value of x depends on the exponent portion. And so the exponent, that's the A1 to A11 part. If they're not all zeros or all ones in those 11 spots, then we have what is called a normalized floating point number. And the value of the number would then be plus or minus, depending on what the sign of the value is, then 1 point. Then we have the mantissa part, the B1 to B52. And all of this is treated as a number in base 2. And then we multiply that by 2 to a power. And in the case of a normalized number, the power is the A1 to A11 as a binary value, and then we subtract 1023 from that. And the 1023 corresponds to one of the values in base 2. We see the 1024 showing up as a particular position. And this has to do with making sure that the spacing of the numbers is correct. So this 1023 is called a bias, and it is used to make sure the numbers relate to each other in a nice way. We won't get into the details on that. And this isn't something that we're going to do by hand. We're not going to do these calculations. But this is what's happening when you have a number that's stored in the floating point format. The A's that are those 11 values and the 52 values are then put into different positions in terms of what is the meaning of this actual number. If the exponent is all zeros, then the number x is a subnormal floating point number. It's not a normalized number. And in that case, the part to the left of the binary point is the 0 here. The b's are still in the same position. The a's are still in the same position. There is a difference that rather than subtracting 1,023, 1,022 is subtracted from there. If the number A1 to A11 is smaller than 1,023 or smaller than 1,022, then the exponent is negative. If it's bigger than 1,022 or 1,023, then the exponent is positive. So this allows us to get the bigger numbers and the smaller numbers, the ones that are closer to 0. So in these two cases, we have these normalized floating point numbers, and then we have these other floating point numbers that we can also describe. If the exponent portion is all ones, then there are three options that are available. If the x corresponds to a positive infinity or a negative infinity, that depends on the sign that's in front, then we use INF or negative INF. Or there's a situation for something that is not a number, and that is recorded as NaN. And the not a number situation would happen if the b's are not all 0. And so this idea, you don't have to worry about the details, but the idea of a positive infinity, a negative infinity, or not a number, the idea is we're trying to make sure that things are meaningful and that we're not doing things like raising 0 to the 0th power or other kinds of things that don't make sense mathematically. And so the not a number rules out some calculations that we should try to avoid because they're not clearly meaningful mathematically. But the positive infinity, the negative infinity calculations are all stored in this calculation, or in this representation. We're not actually doing the calculation at this point. We're just looking at what are the symbols in these particular spots. If the symbols look like this, or if the symbols look like that, then here is the meaning. Here is how the system is supposed to interpret that binary number, that 64-bit binary representation. All right, so still in this situation, there are numbers that we can't represent exactly. We need to round them. And the standard describes multiple ways of doing rounding. So as with any other number, floating point numbers can be rounded up. In decimal numbers, we're looking for things that are 5 or bigger at the end, and we round things up in that case. We round down if it's smaller. The rounding up or down corresponds to a binary representation instead of the decimal representation in this particular case. But there's also the idea that we will sometimes round towards 0, and sometimes we round what is called towards the nearest. And so we'll take a look at a couple of situations in that case. So our round, let's think of a function that we call round that will take the value that we're looking at and output the correct value if we have to round up or down or how we're going to round. All right, so round, if we're outside the range, then round is going to round the value down to negative infinity if it's less than the smallest negative number, or round it up to positive infinity if it's larger than the largest positive number. So in the floating point system, positive infinity and negative infinity can be thought of as numbers themselves. And mathematically, they're not numbers. They are representing a direction that you're going, but in this particular situation, we store a particular value, and this particular value means infinity, or it means negative infinity. And so the round, things that are outside the range of the normalized values, gets treated appropriately. Towards the nearest is probably the most common rounding version. And so toward the nearest means that we have a value that we can't represent exactly, but there are two other values, one on kind of each side of it, that we can represent exactly in our 64 bits, let's say. And so we would just round to the nearest one of those. Except sometimes we have a value that's exactly halfway between its neighbors, and in that situation, we have to have more detail. Now, again, this is all specified in the standard. In the case of us using Python, this is all implemented in the language. We don't have to do these calculations. We don't do these pieces ourselves. But this will help explain why sometimes we get weird answers, or answers we didn't expect when we do certain calculations. Why did we get that answer instead of some other answer? And then later, when we're analyzing algorithms, we can anticipate, okay, there's going to be rounding, and here's what's going to happen. So my answer is going to be wrong, but it's going to be wrong in this very specific way. And so in that situation, even though the computer is going to give us the wrong answer, we can still know things about the correct answer based on what we know the computer did behind the scenes. Again, we're not going to get into those details now, but the idea is if we're halfway between the neighbors, there are a couple of ways to decide between the two, which way do we go? And one of those is called the ties to even. So ties go to that you round to the neighbor with an even value as its least significant bit. So only one of these will have an even value as its least significant bit, and you just go to the one with that situation. And then there's a scenario of rounding where we round away from zero. So if we have positive numbers, no matter what, if you're between two things, if you're exactly halfway between, you always round away from zero. So that would mean rounding up for positive numbers. But if you had a negative value, then you would round it down. And so the ties away from zero is a common way of breaking ties at the halfway point. So positive numbers that are halfway get rounded up. Negative numbers that are halfway between the two possible values get rounded down. All the other numbers get rounded toward the nearest, so that would be the idea of what happens in decimal values. If you had something 0.5, do you round it up or do you round it down? Well, if your number's positive, you round it up. If the overall number was negative in this ties away from zero approach, you would round that down. So the idea that happens is, as long as it's specific and as long as it's clear of how the rounding is working, then we are able to utilize that and be able to analyze to know and understand what is happening, what is going correctly, what is going incorrectly. Okay, so in comparing these two real numbers, we have a smallest positive value in the IEEE double format. And this comes from filling in the values in the representation in the description. And so the smallest positive value is 2 to the negative 1,022nd power, which is about 10 to the negative 308th power. So that's a very small number, and that's the smallest value that can be represented. Smallest positive real number, there isn't one. We can always find a smaller positive real number. Whatever positive real number we had, divide it by 2, and that's closer to 0 still. And so there's always a smaller positive real number. We can't represent infinitely many numbers in a computer. We can always only represent a finite number of them. All right, there is a largest value in the IEEE double format. The largest value, fitting in the pieces that are described in the standard, gives us a number that's about equal to 10 to the 308th power. The smallest value overall would be the negative of that, right? Negative 10 to the 308th. And in both cases, there is no largest or smallest real number. So again, the floating point format doesn't correspond to real numbers. Now, even if we went to the 128-bit representation or the 256-bit representation or any other representation that we wanted, the largest and smallest values get larger and smaller correspondingly, but they still have a limit, and so they're still not exactly representing real numbers. Now, gaps between numbers, machine epsilon is the description or the name of the gap between 1 and the next largest floating point number. And in the double format, that number is 2 to the negative 52nd power, which is about 10 to the negative 16th power. And so you'll see, like, for instance, in Python, that numbers are usually represented to 16 or 17 digits after the decimal point, and that corresponds to this idea of beyond that, you can't trust the numbers anyway, because the machine precision only goes out that many decimal places. There are no gaps between real numbers at all in terms of when we say a gap in the double format, what we're saying is there is no number between 1 and the next value that you can represent. There is a gap in those values. In the real numbers, you could always just average the two ends together and there's a number in between, and then there's a number in between those, and numbers in between those, and more and more and more numbers. But representing these numbers computationally, if you needed a number that's in that gap, you have to use either rounding up or rounding down, rounding one way or the other, and use that value instead, so you won't have the exact value. On the count, we mentioned this idea of something called uncountable. There are different infinities. Well, again, we'll talk about that later. Countable kinds of infinities and uncountable kinds of infinities. The real numbers themselves are in that uncountable category. There are finitely many floating point numbers, and you will get a chance later to do that count and determine how many of these double format floating point numbers there are. So think about the numbers, think about how they're represented, and see if you can count how many floating point numbers there are. It's a large number, but it is a finite number. And then there are some other things. Mathematically, we know that you can add two numbers together, and it doesn't matter which one you add together first. We have the commutative property there. And there's another property that involves dealing with three values at a time called the associative property. And so we're going to take a look at an example where we will see that in general, the double format is not associative, but real numbers, it is associative. So what that means is that when we're doing calculations with a computer, we have to be careful of the order that we do the calculations, how we do things, because if we change the order around, we can get different answers. So for real numbers, if we have three values, A, B, and C, and let's say we're just going to add them, we have kept the order the same, A, B, and C from left to right, but we're saying, hey, let's do the A plus B part first and then add C. Or let's do B plus C first and add A. Well, mathematically, we get exactly the same answer. There's no distinction at all. But in this example, we're going to use the simplified version so that we can see it more readily. In the simplified version, if we took these three values and did the calculations with those values, we have to do our calculations in our floating point environment. So when we say let's calculate a plus b, that means let's do that in the floating point world in this case, in our simplified toy version. So what would happen? We're going to add x and y together in the format that we have. Take that answer and add the z to that in the same format. And when we do that, we get 1.10 times 10 to the negative second powers. You could make sure you understand that calculation, do that calculation. What we're doing is we're adding the x and the y and writing that answer in the simplified version. And then we add the z to that and write that answer in the simplified version, and we end up with 1.10 times 10 to the negative second power. But if we do this in the other order, do the y plus z first, do that calculation, and then add the x to it in that format, then we only get 1.00 times 10 to the negative second power. And we notice that here we have different answers, and it depends on the order that we've done those calculations. So anytime we have floating point numbers, it really does matter how we do the calculations. So we're going to solve an equation, and we're going to use the full IEEE standard in this calculation. And so the equation that we're going to solve is we're going to look at a quadratic equation. And our task is we're going to find the smaller root of this particular kind of quadratic equation. It's not a general equation. This is a very specific type of equation. It's a quadratic equation where the leading coefficient is 1. So we have x squared minus 2px minus q equals 0. And we have the condition that both p and q are positive in our calculation. So we know there's a quadratic formula that applies in all cases, and we're just going to look at this one very specific type of quadratic equation to see what can go wrong, to see what can happen. And what we're going to do is we're going to, in our particular case, is we're going to let p be this very big number. Will this be 12,345,678? And we're going to let q be 1. So the p and q are very far apart in values. P is very large relative to q. They're both positive numbers. They both fit in the situation. But we're going to solve the equation and find the smaller of the two answers to this quadratic equation. All right, so if we apply the quadratic formula to this, and you want to look that up if you don't remember, or if you do remember, then make sure you go through the steps. We're not focusing on the algebra itself, but that this is a way to solve this. If we solve this equation and look at the smaller root, the answer is p minus the square root of p squared plus q. So we have this value, and when we apply this particular choice of p and this particular choice of q, the answer that we get looks like this. Now in Python, the 6, there's an extra digit that it outputs in terms of the way it's represented and stored behind the scenes, and so that is probably a 5.5 there if you use Python. But the idea is that this is the answer that if we apply the quadratic formula directly to the equation, mathematically, this symbols are the exact answer, and using Python to calculate, this is the answer that we would get back. Now there's another method that involves doing something slightly different. We're not going to get into the details, but it's still applying the quadratic formula in a sense, but then rewriting it in a slightly different way. And in that case, the formula would say that the smallest value is this negative q divided by the sum p plus the square root of p squared plus q. And if you do that version, if you write a function to do that version in Python and give it p and q as the input values, then we get an answer that is also negative 4 point something, and there's a 10 to the negative 8, but almost all the other digits are completely different. And so both of these mathematically are exactly the same, but computationally they're very, very different. So how do we know which one is correct? Which of these two approaches is the correct answer? In this particular case, it turns out that method 1 is trying to calculate this number, which is a very small number. 10 to the negative 8 means we have a very small number here. And so it's trying to calculate a very small number by subtracting two very large numbers. P squared plus Q and the square root of that is almost the same as P. So you're trying to find a very small number by subtracting a large number from another large number. And so what happens is you get this idea of what's called catastrophic cancellation. And what it does is results in a number that has almost no correct significant digits. You had a big number and you subtracted another big number, and an awful lot of information got lost. On the other hand, method 2 tries to find this very small number by dividing a relatively small number by a much larger number. And in this particular case, it gives an answer that is correct to the full machine precision. If you work this out line by line by hand and did this calculation, this number to full machine precision is the correct value under method 2. And so what that means is when we have, say, two equivalent mathematical ways to do something, that does not mean that we're going to get the same answer if we apply those two different methods computationally using the computer. It doesn't matter. We're not talking this is a limitation of Python. We're not talking this is a limitation of any particular programming languages. This is a limitation of the way numbers have to be stored inside of a computer. There's only a finite number of things that can be done, a finite number of things that can be represented, and so there will always be mistakes in the answers. So we have to be really, really careful. If mathematically equivalent algorithms can produce different floating point results, we have to be careful to know, hey, which of these is most correct. In some cases, the floating point answers are close enough that it doesn't matter. They would say, okay, well, we're off just a little tiny bit. It's one digit way over there somewhere, slightly wrong. That's okay. We can deal with that. But sometimes those results are drastically different. So what would happen if, for instance, in the example that we just looked at, if we were looking for 1 over the answer, how similar would they be if we took the answer from method 1 and did 1 divided by that answer and compared to 1 divided by the answer from method 2? So the answers can be very, very different in the two cases. And even if the numbers aren't so far apart, look at the previous example, the equation that we had, and rather than having that really large value for P and the big difference between P and Q, try to solve that equation when P is 2 and Q is 4. So use Python to test that same equation, but put P equals 2 and Q equals 4, use the same two formulas, and see whether you get the same answer. And as usual, feel free to ask questions in the comments, by email, or on Discord. Have a great day.